In this video, I'm going to talk to you about the second derivative test. So while the first derivative test checked for regions of a function that were increasing or decreasing, the second derivative test checks for regions of a function that are concave up or concave down. Concavity is a characteristic of a function that describes the behavior of its derivative, whether it's increasing or decreasing. So in reality, it's the first derivative test just applied to the first derivative. So if the first derivative is increasing on some interval I from a to b, or the second derivative is greater than 0, then f of x is defined as concave up. The region of a graph that's concave up will look something like this. And concave down is the exact opposite definition. So if the first derivative is decreasing on some interval a to b, or the second derivative is negative, then f of x is defined as concave down. And a region of a graph that's concave down will look something like this. By the way, these graphs represent the shape of f of x when the graph is concave up or concave down. When the graph of a function switches from increasing to decreasing or decreasing to increasing, we call those transition points critical values or extrema. We also have a name for points when the graph changes from concave up to concave down. These are called points of inflection. The way we find the points of inflection of a graph is exactly the same way we use to find the critical values of a graph. But instead of setting the first derivative equal to 0, we set the second derivative equal to 0. And so now we're going to use everything we just covered in the video to do the second derivative test. We're going to find the intervals when the function f of x equals x cubed minus 9x squared plus 24x minus 18 is concave up or down. The way we do the second derivative test is exactly the same as the way we do the first derivative test, except we're finding POIs and we're testing the sign of f double prime. Because of that, I'm not going to go over how we set up the test again. You can watch the first derivative test video for that. We begin by finding our points of inflection, and we do that by finding the second derivative. Here's our first derivative, and here's our second derivative, and we set this equal to 0 and solve for x. I add 18 to both sides. We see that x equals 3 is the only POI of the function. Now we're going to make our intervals, and just like how we cut up the number line using our critical values in the last video, we're going to do the same thing, but with our POIs. So we only have one POI, which is x equals 3, so there's going to be two intervals. First going from minus infinity to 3, and the second going from 3 to positive infinity. Here we turn to sign chart, which is really helpful in organizing information when doing these kinds of tests. And it doesn't matter what you pick, so long as your values are in each of their intervals. Here I'm going to pick x equals 0, and here I'm going to pick x equals 10. Now we're going to check the sign of f double prime when x equals 0 and when x equals 10. We see that f double prime of 0 is negative 18, which is negative, so we're going to indicate that in our chart. And we see that f double prime of 10 is positive 42, which is positive, so we indicate that in our chart. Now, time for our conclusion. We see that f double prime is negative in the interval minus infinity to 3, so we know in this interval the graph is concave down. And in this interval, f double prime is always positive, so we know this is concave up. But unlike the first derivative test, we don't do any more analysis in the middle or at these POIs because the POIs just stand for POIs. They don't mean anything else. That's how you do the second derivative test.